Hi everyone, welcome to my home office. Thanks for joining this talk about Kotlin. I won't be talking about Kotlin the language or any of the Kotlin frameworks, but I'll be talking about what Kotlin looks like after it has been compiled and added into your application. Um, this is mostly out of curiosity, but it also has practical applications. It may help you to learn something about your own applications that you develop and release and how they are processed and run on an Android device. I'm Eric. I'm the founder and CTO of GuardSquare, and I'm the original creator of ProGuard, the optimizer and obfuscator that you may have used before for your own applications. We currently maintain ProGuard as part of our work at GuardSquare. So in this presentation, I'll touch upon a couple of topics. I'll talk about Kotlin aspects, of course, the Kotlin runtime libraries that go into applications, the bytecode that the Kotlin compiler generates, and the metadata that the compiler adds to the application. And then I'll talk about how all of this interacts with any optimization and obfuscation that you may apply in your application. So I'll look at some of those results. Throughout the presentation, I'll be using looking at the Google I/O scheduling app as a sample. This is a well-known app, and in its latest version, this is entirely written in Kotlin. So it has about 300 Kotlin source files, and it relies upon more than 100 libraries. All of that amounts to 176 jar files, which contain Java bytecode, of course, and those bytecode files are compiled onto Dalvik bytecode files. In the debug version, that's about 16 DEX files amounting to 24 megabytes. All of that gets packaged in the final APK, which is about 13 megabytes in its debug version. So it's smaller than the DEX files combined because the DEX files, of course, can be compressed. Let's look at the Kotlin libraries first that go into this sample application. If you develop in Kotlin, of course, you'll need the standard libraries, the standard library common, and they are 1.4 megabyte, 180K. This application also uses coroutine, so it needs the additional coroutine library, which is another 1.5 megabytes. All in all, it's not entirely nothing, but compared to the size of the complete application, that's not too bad. In addition here, of course, the library or the application is using a lot of Android functionality and Android libraries. And many of those libraries nowadays have Kotlin extensions, some sort of wrapper for the libraries that allow you to use them in a more Kotlin way, using the Kotlin idioms. There are many of them, but they are all small, just a couple of tens of kilobytes. So looking at this compared to the size of the entire application, it's not so bad. It's just a small overhead in size. Then I'm looking at some of the constructs that you typically use in your Kotlin applications. So we've looked at the libraries now. Now in your own applications, you'll probably use some of the constructs, and I've singled out three important ones that many applications use, starting with the simplest one that I could find, type aliases. So in this example from the sample application, there is an alias defined that equals to a slightly more complex type. And that alias is used as a parameter type in some function elsewhere in the application. Now, if you look at the compiled code and disassemble it to make it more readable, you can see that the type alias has been replaced by its original definition. So all in all, there is no overhead here. As expected, the type alias behaves like a macro, and it's just replaced in the code. So there's no harm in using type aliases clearly. So that's a simple example. Then moving on to another very common construct in Kotlin, data classes. These are classes that allow you to very compactly write something to represent data. In this case, the application contained a room class that has two properties, ID and name, both strings, and a derived property that is an abbreviated name. As documented in the Kotlin documentation, this is of course expanded to more elaborate Java bytecode. If you look at the decompiled or disassembled bytecode, or at least the headers there, it's more or less as what you would expect. The properties have been translated into fields, and there are getters associated with them. Also, the additional property here. In this case, it's an immutable class with read-only fields, so you only have getters. There is a constructor with two arguments, and maybe a bit less well known, there are also a few additional methods, two component methods that actually correspond to the getter methods. They just have a different standardized name, and this name or these methods, they are used if you deconstruct any instances of this room class. So irrespective of whether you do that deconstruction anywhere in the code, these methods are generated in your compiled data class. In addition, there are a couple of copy methods that allow you to create related instances, similar instances of this instance of the room class. And finally, as documented, the Kotlin compiler will create the toString, hashcode, and equals methods for you to make life just that little bit more convenient. Again, these methods are created whether or not you are actually using them in your application. So there's a little bit of overhead here, but we'll see later on in our analysis whether this has any effect in the final result of your application. And then as a third example, I'm looking at null checks in the generated bytecode. So as you probably know, the Kotlin language is aware of nullability of types, unlike the Java language or Java bytecode. And to help you with that, it adds some sort of assertions in the bytecode. And this is what you see in disassembled bytecode. For instance, in the constructor, at the beginning of the constructor, there will be two assertions that ensure that the parameters, ID and name, are really null or never null at runtime. So in theory, this shouldn't be necessary if all of your code is Kotlin because it's aware of nullability. But perhaps you're mixing your Kotlin code with Java code, and then it's useful to have some seatbelts that keep accidents from happening here and really ensure that the contract is obeyed. A small note here is that the names of the fields or the names of the parameters are hard-coded as strings here. So that's an interesting aspect that we'll see again later on. The check itself makes use of the intrinsic class in the Kotlin runtime. So this is part of the small library that you have added. So we've added these libraries. The Kotlin compiler has added some additional code. So it's interesting to know what happens if we start optimizing this application. And this is what we do in the standard way. We enable minification, so that enables both optimization and shrinking and obfuscation. And by default, you'll now get the R8 compiler to handle that for you. If you want to use ProGuard instead of R8, at this point, you can still switch back by enabling it in the Gradle.properties by setting one of these properties. Of course, ProGuard is still my favorite open source project, so I've done most of my tests with ProGuard for this presentation. The first thing you'll see if you enable ProGuard, and this is true for any project, whether you use Kotlin or not, is typically a series of warnings that ProGuard spits out. about things in the code that don't look quite proper. So typically missing dependencies because you've added some libraries to your code, but they depend on other libraries that are not present, and they may not be present because they're not used. You get similar warnings here if you use Kotlin, but these are a bit more mysterious in the sense that some very obscurely named class seems to be referring to another obscurely named class, and that latter class isn't present in the code. Looking at the bytecode, studying the bytecode, this actually seems to be true. So this class has some metadata, and that refers to this other class that really is missing from the application. In practice, it's not a problem, and it's just an artifact of the Kotlin compiler that over time will get solved, I'm sure. But for now, you have to live with it and tell ProGuard that it's all okay. You have to reassure ProGuard by using the don't warn option, and that's what you often do with these warnings. You say that all of these methods that have this inlined part in their name, they may have some slight problems, and ProGuard can just suppress the warnings and continue processing, and everything will be fine. So what do you get if you've optimized your app? Well, initially we had this 16 DEX files in our applications, and this is reduced by about 73% to a single DEX file that is a lot smaller. So this is a good indication that it's very useful always to apply optimization and obfuscation to your application if you intend to release it. Many users will appreciate having a smaller app. In the final APK, this results in a reduction of about 55%, still a very good improvement. Now, of course, not all of this is due to Kotlin being used here. This is mostly because your application or this application contains a lot of libraries, but the application doesn't use all of the functionality that is present in these libraries. It's probably not using many classes or fields in those classes or methods in those classes. And ProGuard and R8 will analyze your code, identify those classes, fields, and methods, and simply remove them to get this smaller bytecode. In addition, ProGuard and R8 will apply optimizations to the individual instructions in the classes. They will propagate constants, maybe remove parameters, all these kinds of small optimizations that may even improve the performance of your application. And in addition, they will result in a small reduction in size in the Dalvik bytecode. So those are some nice results to start from. Of course, I want to verify how much of the Kotlin code is affected. The Kotlin code that I talked about earlier that is generated or inserted in your application. And it's pretty much as expected. So the room class, if you look at it after optimization, it still has the fields, of course, representing the ID and the name of the room. But the getters, they are all removed. And in this case, it's not so much that they are not used in the application. They are used, but the optimization step has been able to inline the getters and as a result also remove their definitions. So that's why they are gone in the room class. In order to be able to do that, it needed to make those fields public. So they were private before, but they are now public. That's not something you probably want to do for an immutable class in your nice design in your source code, but we're talking about a final application now where we want to make it as small as possible and as efficient as possible. Furthermore, the constructor that has these two arguments, it's still there. And then the component methods and the copy methods, they were actually unused in the application, so the optimization step could simply remove them. Finally, there are these toString, hashcode, and equals methods. they are still present in the processed bytecode. And this is a bit unfortunate, perhaps, but this is a very difficult problem. These are methods that override the corresponding methods in the object class. And for an optimizer, it's very difficult to analyze and figure out to ensure that these methods aren't used at runtime. So for instance, hash code, it's obvious that it's necessary if you add a room class to a hash set or a hash map, perhaps. But if you add it to an array list, for instance, and you print out the array list, the toString method might be used without that being very obvious from the code. So in general, and this is for most of these classes, it will be impossible to determine that these methods aren't used, in fact, and they will still be present after processing. Then the other construct that I talked about earlier, so the null checks that were inserted. And this is what they looked like originally. There are two different possibilities here. On the one hand, it's possible that ProGuard is able to analyze all of the code, and it can ensure that the strings that enter here as parameters are never null. And then it might be able to figure out that this check will never throw an exception and that it's unused and unnecessary, and then it can remove all of the code that is associated with it. In general, that might not always be possible or that easy. So in that case, you might want to give ProGuard or R8 a hand by telling it that we don't care about these checks. We know that our code is perfect, it doesn't contain any bugs, and it can get rid of these assertions. And the way to do that is to add an option assume no side effects to the ProGuard configuration, where you tell ProGuard that these check methods will never have any side effects. In this case, they will never throw an exception, so that ProGuard can remove all invocations and eventually also all of the method definitions. A more compact way to write this is using wildcards. You can say all of the check methods that have any number of arguments of any type. Feel free to remove them. Of course, we need to check that if that's really happening, and indeed, in the constructor of the room class, these assertions have been removed after specifying these assumptions. Now, there's a reduction in size, of course, because of this. And to be honest, I was a bit disappointed here. It's just a reduction by 32 kilobytes. It's always nice to know that the calls are gone, but the reduction is relatively small. Of course, part of it is due to only a small part of the application here, of the entire code base here being Kotlin code. So that might be more for entire large Kotlin applications, but it's not so enormous. Of course, it always gives me a warm feeling to know that the calls are gone, and at least at runtime, you don't have that small overhead of these checks being executed. Okay, so so far I've been talking about bytecode, so the bytecode that the Kotlin compiler generates. But the Kotlin compiler also generates metadata for all of the constructs that it offers. And I'll go into a bit more detail about where and how it stores those, just to give you an impression of what's going on there. Why would the Kotlin compiler add these metadata? Well, there are essentially two use cases. On the one hand, you may be writing code for a Kotlin library, and that Kotlin library might be used in other Kotlin applications. And for that use case, it's necessary to have these metadata so that the Kotlin compiler can actually use the Kotlin idioms that you have in your library. In theory, the information would be there in just the bytecode that I've shown before, but of course, metadata can help a lot to make sense of the structure. In addition, the second use case is reflection. And this is not just the traditional Java reflection, but this is the additional Kotlin reflection that it offers. And I'll show a couple of examples of that in a moment in later slides. First, I'll dive a little bit deeper into the technology, the representation that's behind these metadata. And this is mostly, again, out of curiosity, but it's nice to know where everything is stored. If you look at a Java class file, it has a very standard structure. It's very easy to decompile or disassemble as a result. As you might expect, there is a version number in it. It specifies for the class the superclass, its interfaces. It has a whole list of constants like integer constants, float constants, classes, method references, and so on. And as you would expect, it contains the fields that are in the class. It contains the definitions of the methods that are in the class, including the bytecode associated with these methods. And finally, it contains a number of attributes. And these attributes are often optional components of a class, like the source file name. So stuff that is useful for debugging purposes often. And this format is standardized, and it's of course understood by the Java compiler that generates it, or the Kotlin compiler that generates it from Kotlin source code. And it's also understood by the Java virtual machine, which executes the bytecode. And it's understood by the D8 and R8 compilers, which transform the Java bytecode into Dalvik bytecode, which is functionally equivalent, but yet another different format. Now, the class file format is something that's governed by the Java community process, and it's evolving only very slowly. So every now and again, you get a new version of Java, and it may add an occasional new constant or an occasional new attribute that is then understood by all of these this software surrounding it, the whole ecosystem. Now, JetBrains with the Kotlin language, they are moving a lot faster, of course. So they don't control the Java community process. So what they've done is add the Kotlin metadata in the form of an annotation. And an annotation is actually just another attribute here. And if we look a bit closer at what this annotation looks like, it actually has a deceivingly simple definition, which looks a bit like this. It looks quite basic, but then if you start looking a bit closer, there is a whole world behind it. There can be different types of metadata, and the data themselves are stored mostly in these arrays of strings here, where the first array contains protobuffer data, or data in protobuffer format. So that's another format entirely hidden inside the annotation. And these protobuffer data, they may be referring to strings that are available or present in the second array of strings. So although this looks simple on the surface, it's actually quite involved, quite complex. And to help you with that, JetBrains has kindly, or to help anyone working with the metadata, JetBrains has kindly made available a support library, a metadata library, to work with these metadata. So they bring all of this up to a higher level of abstraction that allows to work with the metadata without having to know all of the details of the protobuffer format, for instance. And that's quite convenient already, of course. That's just a library still, so you need to write code around it. And that's what we've done. We were interested in the metadata inside, and we've written an application on top of that to actually examine the metadata that are present in your APK, in your classes.dex files, in your bytecode. And it comes in two shapes. On the one hand, we have an online tool that allows you to upload your APK and browse through all of the classes in the APK, and then for each class, see the Kotlin metadata that are associated with it. In this case, the room class, if you browse to it, you can see all of the properties pretty much like they're defined in the source code. So what is important to mention here is that this is essentially all of the information that's just in the metadata. It's the tool doesn't need to look at the bytecode. It just looks at the metadata that is associated with the bytecode or tagged onto the bytecode to find all of this information. So as I mentioned, there is a whole world of information hiding behind these small annotations. I mentioned that this code, this tool, comes in two shapes. So we have the online tool where you can upload your application, but it also comes in the form of an open source project on GitHub that you can download yourself and compile, and that you can then run on your own applications to get essentially the same information. So far, I've talked about the bytecode, the metadata that are tagged onto the bytecode in the form of annotations. And there's a third or another form of metadata in the form of metadata files that some source files may generate. And these are the files that you may encounter in your APK as well. I won't go into detail about those further. But I'll move on to reflection, as I've promised before. So how does reflection relate to all of this bytecode and metadata? So you're probably familiar with reflection in Java. And in its simplest form, there is the class for name construct that takes an argument as a class name. And in some cases, the class name is just a simple string constant that is easy to deal with. ProGuard can do that. But in many cases, this is just a variable, and it's at build time, it's impossible to figure out what kind of name or which names can be passed in here. And that's the case where you need to have these famous or infamous keep options in your ProGuard configuration that tell ProGuard to keep the mentioned class here with its original name, so that a construct like this will still continue to work at runtime after it has been optimized and obfuscated. And there is a similar concept in Kotlin. So Kotlin has its own types of reflection. And I've shown a couple of examples here. You can ask a class for its qualified name. You can ask if a class is a data class or not. You can ask for its member properties, and there are a couple of more of these constructs. And this is actually a case where the Kotlin runtime, the reflection runtime, not only requires the bytecode like Java, but it requires the metadata that the compiler has inserted. And of course, it requires those metadata to be consistent with the bytecode. And that is not obvious, of course, as I've shown. The metadata are in a non-trivial format, and you have to make an effort to make sure that everything remains consistent. And that's what we've done. We've done that in ProGuard version 7.0, where you have to specify, you still have to specify that you want to keep a class with its original name. And there is a simple option to specify that you want to keep the Kotlin metadata. And then it will keep all relevant Kotlin metadata. R8, as of version 4.10, has similar functionality. You have to keep the original class still, and then the annotations in which the metadata are stored, and the metadata annotation itself. And I'll show effect you get in your application if you start obfuscating your Kotlin application now. So first looking at the bytecode. So as you remember, there is bytecode and metadata. I'll start with the bytecode. This is what the bytecode looked like, at least the headers of the bytecode, the fields, the getters, the added methods, and the standard added methods. And if you now look at the obfuscated version of that bytecode, this is essentially the same as Java bytecode. As you would expect, the class names are short names now. The field names are short names now, A, B, ABC for method names as well. The constructor has changed name. And here, maybe the small special thing is that the method that had default in its name still has default in the name, because that's necessary for Kotlin to function properly. And as usual, as for any Java or Kotlin application, the toString hashcode and equals method can't be renamed, otherwise you would break the consistency with the class Java lang object, which has these names. So that's pretty straightforward. There's nothing special here. If you look at the obfuscated bytecode, the null checks that I talked about earlier, this was what the code looked like originally. And you may remember that these parameter names are hard-coded. If you look at the obfuscated version of this bytecode, the parameter names have been obfuscated as well in ProGuard. And last time I checked, R8 doesn't have this functionality yet. So if you care about hiding the names of your fields and parameters, it may be worthwhile to try ProGuard here. Similarly, the toString method, it has this generated code that reveals the name of the class and its properties. And if you apply ProGuard to it, it's now able to also obfuscate these hard-coded strings in your code. Then the metadata. So this was the bytecode, the metadata, which is a bit more challenging. If you look at the original metadata, this is what they looked like. Looking at it with the metadata viewer that we had. And if you look at the obfuscated version of those metadata, this is what you get, and it's consistent with the bytecode. So that's pretty much what you would expect, or at least hope for. So that concludes the technical part of my presentation. If you're still curious and you want to learn more, there are a couple of interesting blogs. There is a blog by Jake Wharton where he optimized an application, optimized all of the code until it got really a lot smaller, significantly, and he even suggests a couple of tricks to use standard Java classes instead of the Kotlin utility classes to even reduce the application further. So that's a nice idea. There's another nice blog by Florina Muntenescu, where she investigates that the effect of inlining functions, which can sometimes help the Kotlin compiler to reduce the code, remove some Lambda functions that it would need otherwise. It's a bit technical, but very interesting blog. And finally, there's the blog from Google's R8 team, where they describe how they've enabled Kotlin support in the R8 compiler. If you really want to try out more, of course, you can look at the Kotlin metadata printer that I've discussed. This is the URL for it, for the online tool, where you can upload your APK and browse through all of the metadata. Or you can download the open source project, compile it yourself, and look at your metadata on your own computer. If you really want to get your hands dirty, you can also look at JetBrains' metadata library that allows you to disassemble or explore the metadata that are inside Kotlin annotations. If you are interested in the combination of Kotlin metadata and Java bytecode, and you want to read, write, manipulate them, you can have a look at the ProGuard core library. So now supports Kotlin metadata as well, using JetBrains metadata library. And it allows you to keep everything consistent, manipulate things. It's the basis for ProGuard, and it's the basis for our Kotlin metadata printer. Just to give you an impression of what the code looks like, this is a simple snippet of code. It uses the visitor pattern, and this piece of code visits all classes in a given class pool. It then applies a name filter, only visiting the mentioned class, the room class. In that room class, it visits the Kotlin metadata, and for the Kotlin metadata, it visits all functions, where it applies this small lambda function, which prints out the name. So this piece of code prints out all of the functions in the Kotlin metadata of the room class. So this is how compact it can be. So in conclusion, I've talked about Kotlin's runtime libraries, the bytecode that it generates, the metadata that it generates inside the bytecode and alongside the compiled files. Of course, that increases the size of your applications, and it also leaks some naming information about the application. But you can mitigate that by optimizing your application and applying name obfuscation. So as a final slide here, we have a few minutes for questions. But if you still have questions after that, you're welcome to visit our Guard Square community, where you can talk to our engineers, including the engineers who have worked on the Kotlin support in ProGuard. So that concludes my presentation. Thanks for joining me. Thanks for staying with me. And we now have time for a couple of questions. So a first question, if R8 can't handle obfuscating methods, why use it? Why not stick with ProGuard? Well, as I mentioned, the latest version of R8 can obfuscate methods, and it can obfuscate the corresponding metadata, so that, for instance, reflection will still work properly. It's just that last time I checked, it doesn't obfuscate the toString method that reveals some information from the generated code. And then another question from Matt. I mentioned Dalvik bytecode. What about art? Of course, Dalvik bytecode is what goes into your APK file, and that APK file gets uploaded to the Google Play Store, or at least downloaded to any device, including art devices. And it's only on the final device that the Dalvik bytecode gets compiled on to or in art with a just-in-time compiler. So as far as we are concerned in the build process, we're only interested in the final Dalvik bytecode. How do build times compare when using R8 versus ProGuard? That depends a lot on the settings of ProGuard. So by default, it applies in the Android build system 5 optimization passes, which is quite a lot. And as a result, it's generally slower than R8. But a small tip here, if you say optimization passes 1 or optimization passes 2 in your ProGuard configuration, it will actually typically be slightly faster than R8. So I think that's all the time we have, but thanks again for your attention. Feel free to get in touch if you want to learn more. Cheers.